Hi, welcome back to the channel. I'm back again with a video. This time around, we are picking up from where we ended and we are going into calculus, and specifically, we're looking at differentiation. So, what I want to do in this video is to explain the whole idea about differentiation, okay? And yeah, where it comes from and how you go about it, okay? Now, if you can look at what we've done in the previous videos, where we've been talking about the equation of a line, uh, yeah, how to get the gradient of a given line. Remember, we are saying something like, or if you didn't watch the videos, you may know this already. To say, if you have an equation of a line, for example, if you have got y is equal to 3x plus 7. Okay, you can easily look at this equation and say, okay, since the general format of a linear equation is mx plus c, you can easily say, okay, this here is my constant, and this 3 here is my gradient. This is the m actually here. So here you are saying this is like your gradient, the m, and the 7 here is the constant. So if in the case of a linear equation, it's easy. You can easily like point out what is the gradient of this line. Now, out of in a cave like this, okay. Now, in a cave, remember a cave is different. Okay, you can't talk about something like the gradient of a cave because if you look at this, like it doesn't have the same gradient. If you look at, for example, this point here, if I can mark some point here, if I can look at, if I say this point here and this point here. So if you look at this point and this, these 2 points cannot have the same gradient. You can tell that here the slope is kind of more steep. Okay, the gradient here is kind of higher than whereby here the gradient is kind of lower. If you are to try and put a line that is parallel to this, it would be something like this. Okay, so you can tell to say this line here and a line like here, okay, a parallel line here. We can tell to say if you try to draw a parallel line here, it won't be that much slanting as compared to this one. It's like somewhere else it's like this, and elsewhere it's like this. Now, if you can look at these two, this has got a higher gradient compared to this because it's like one is kind of flat, a bit flat, and then one is like this. Okay, so that's the nature of a curve. So a curve doesn't have the same gradient at any point. It's like every point on the graph can be said to have its own gradient. Okay, because at that point in time, the curve is, it's changing the way it's, going about its slope. So in this case, how do we compute the gradient? We can't talk about the gradient of the curve like we have just said, but what we can say is we can easily say at this point here, the gradient of this line is, for example, something like 2. At this point here, the gradient of this line, okay, is something, maybe say 3. At this point, the gradient is 5, okay? We can talk about something like that because, yes, one thing for sure is this curve doesn't have the same gradient at any point. Okay, every point has got its own gradient. Okay, of course, there could be some points on the graph that may have similar gradient, or maybe one could be negative, one could be positive, but almost sloping at the same rate. But generally speaking, we can only talk about, say, at this point in this graph, the gradient is this much. So when you have got a curve, okay, or if you have got an equation like y is equal to x squared plus 2x, minus 1, in this case, we cannot talk about finding the gradient like what we did with linear equations. In this case, all we can say is, okay, we have this graph. So however it's sloping, it could be going something like this. Then you ask ourselves, what is the gradient at this point? What about here? What about here? What is the gradient? So differentiation helps us to come up with a way of being able to find the gradient of a given equation, which is some kind of a curve. at a specific point. So, for example, you can say, given this function here, what is its gradient where x is equal to 1 or where x is equal to 3? In short, we're trying to say, suppose this point here is 3, then we raise it up here. Where do we reach? Here. So we are saying where x is equal to 3, m of the gradient is equal to what? So we are trying to see if we can establish that. So that's the idea about calculus. That's the idea about differentiation. So now the question comes back. How do you find the equation? How do you find the gradient of a curve at a specific point? Okay, we're going to make some assumptions here. Okay, we're going to make some assumptions here. So I'm sure you can agree with me to say, if I go back to my graph here, okay, let me put a point here. Okay, if I take, for example, this point, so I'm going to refer to this point as A. Okay, now if you want to find the gradient of this point at this point A for this graph, okay, we can assume that, okay, since we don't know, we can't find it like the way we can find for linear equation, what can we do? We can assume that, suppose we drop this point here down here and say, okay, what is the value of x at A? Okay, let's assume that maybe the value of x is something like 4. Okay, then what is the value of y at this point? So what we can do is we can try and go this side here and find something here. For argument's sake, let's say the value of x here, of y here, is something like 5, okay, as an example. But then, so what I have is, this point is like, this is a point like 3, 5, okay, 3, 5. So A is a point 3, 5. So we're trying to see what is the gradient of this line at a point where the value of, the coordinates of the point is 3, 5. Now, we can make some assumptions here. What can help us here? We still can't figure out the gradient directly unless we try to make some assumptions. So what we can do is, okay, the best way we can find the gradient of the line at any point, for example here, is to draw a line that is parallel to this. For example, we can say this line here, okay, if I can put a line like this, okay, so this line is parallel to this. So it's parallel to this. So if I can find the gradient of this line here, then that should be able to give me the gradient of this curve here at this point, because this line is parallel. But again, we don't want to go into the issue of trying to find what is this line, what is its equation. So what we can do is we can make some assumptions. We can make an assumption that, suppose if this was my, okay, so I think I made a mistake here. So this shouldn't have been a 3. Okay, this shouldn't be a 3, but it should be a 4. Okay, so this is supposed to be a 4, like this. Okay, so 4, 5 here. So looking at 4, 5 here. So we can make some assumption to say, one of the ways I can find the gradient is to add a small distance to x to 4 here. So what I'll do is I'll add a small distance here like this up to here, okay? So if I add x, okay, what I'm going to do is, to the x I'm going to add a small distance. So it becomes x plus the small distance I'm going to add, okay, the small distance I'm going to add here, okay, I can refer to it as a change in x, okay. In short, x, this is just a small distance I'm going to add to x to help me find the gradient. And then if I look at this, so I've added a small distance here. So this distance here also, if I plot it going up here, it lands me here on the curve. And then if I can take it this side here, okay, I can take it this side here. What does it do? If I had the y here, in my case, like I'm assuming the y was what? 5. So I'm assuming that to the y now, there is a small again distance added. Okay, so this small distance which is added is, it's like it transforms y to become, now it's now y plus a small change in y. So this symbol I'm using is called delta. Delta, so delta simply means change. So change, I'm saying if I had x as 4, now I'm saying I've added a small distance. I've added, for example, a 0.2, okay? So I'm calling this 0.2 as the delta x, okay? Just like whatever results here, whatever becomes the new distance here by virtue of adding the small margin here on y, I'm calling this as delta y. So here the assumption is that if I can get, since what we are using, remember how we are finding the gradient for a linear equation, it's basically the change, okay, the change in x over the change in y. So if I can find the result of dividing the change in sorry about that, supposed to be the other way around. Okay, so let me remove this. So I'm saying gradient is, it says a change in y over the change in x. Okay, so what I'm trying to say is if I get this here, okay, if I can find the change in y divided by the change in x, that must be able to give me the gradient of this curve here, okay, for this small distance from here up to here. So of course it gives me 2 points here. Let me call this point here, okay, this is point E. Let me call it A2. So if I can find the gradient, okay, between A and A2, then that could be somewhere close to the gradient of this curve at the point where at the point A. Now the only thing here is how much have I taken here to be the margin? How much did I add to the 4 here? How much am I adding to the initial x? If I add something like 0.5, yeah, I could get something close to the gradient. But if I get something like, if I add just something like 0.2, then I'm going to get even something more accurate. And then if I add something like 0.1, I'll be a bit more accurate. If I can add something small like 0.02, then I'll get even more accurate. But if I can add something even very minimal, like something like 0.0002, then I'll get even more accurate. By the time I add something that is very, very small, very, very insignificant like this, okay, let's say I took my change in x, I just add a small distance here, okay, here, so that I only add the small margin here, okay. So if I can use this small margin here to find the gradient, then the smaller it is, then the more accurate the gradient is, okay. So that is a principle that finding the gradient of a line, of a curve plays with. It says pick a curve on the graph, add a small margin, okay. So pick any point on the graph, like for example we picked this point A here. On the A, find what's the value of x there. It's something like 4 as an example. Then to the 4, add the small margin, okay. Whatever the small margin that you add, the smaller that margin is, okay, then the more accurate your gradient is going to be. So it simply says pick any point, then add a small margin, and then try to make that margin as small as possible. The smaller it becomes, the more accurate your gradient is going to be. So then how do we do that? How do we now do those computations? How do we carry out that? So I am going to show that in the next video. If you don't understand all these things, don't worry. As long as you understand how to calculate it, it's more than enough for you to be able to make it. I was just trying to see if I can get you to understand the basic idea behind where all these things come from. So see you in the next video.